Hello, my name is Alvaro, and I am a PhD student at the University of Colorado Boulder. Today, my colleagues and I would like to introduce our new numerical simulation framework aimed at studying the growth and detachment of magnetic bubbles in microgravity. In microgravity, due to the absence of buoyancy, when boiling surfaces or electrodes generate bubbles, those tend to accumulate, creating a layer of foam. That, of course, is harmful for the efficiency of the mechanism because it covers the surface. So in order to develop a passive mechanism to remove this problem, we came up with the idea of using magnets to pull those bubbles from the electrodes and increase the effective surface area. However, this problem remains largely unexplored, and there are several scientific questions that need to be answered before we can develop actual technical implementations, such as which is the bubble departure diameter, or what is the shape of the interface, or which are the natural oscillation frequencies of those bubbles subject to the magnetic field within a magnetic liquid. There have been some previous works, some of them really recently from last year, like this one from Yamasaki, where this problem has been explored in high gravity conditions. But the real issue here is that the incompressible Navier-Stokes equations and the mass-Ball equations that conform the hydrodynamic and magnetic problems are coupled. So you need to solve both of them simultaneously. There is no workaround unless you have extremely weak magnetic liquid. So we need coupled fluid magnetic simulations to really understand this problem and get reasonable scientific and technological results. And that is why we have developed this numerical simulation framework, where we have 5 regions, where we subdivide our domain in 5 regions, assuming axisymmetry. And we basically model our bubble, magnetic liquid, solid, air, and magnet, as you can see in this scheme, and solve all the equations, hydrodynamic and magnetic, using a monolithic, fully implicit Newton-Raphson approach that results in a very efficient numerical methodology. And the outcomes of this are exactly what we need: the bubble interface, the departure volume, stability properties, and natural oscillations, and time-dependent simulations. So to sum up, the dynamic of magnetic bubbles remain largely unexplored, particularly in microgravity environments. And those require coupled simulation frameworks to analyze this problem and get scientific and technological results. And our model is able to produce accurate, efficient, and flexible results, allowing us an unprecedented level of analysis and new technical developments. So thank you for your attention. If you have any questions, feel free to reach out at any of these sites, or if not, you can also watch our extended presentation for COSPAR. Thank you so much.